Welcome and thank you for everyone to join the IPC Education Foundation webinar series. My name is Charlene Gunter-Duplessis and I serve as the Senior Director of the IPC Education Foundation and is accompanied by Aaron Burney, Education Program Manager, who you all know potentially, and he'll be able to assist us later on with the Q&A session for our fantastic host and presenter today on the webinar with a focus on navigating IPC standards presented by John Perry. John Perry is the Director of Printed Board Standards and Technology at IPC. For over 21 years, John has coordinated the development and revision of standards focusing on the design, fabrication, handling, acceptance, and storage of bare printed circuit boards. John also wears a second hat at IPC and coordinates the activities of the Lead-Free Electronics Risk Management PERM Council, which provides a path for aerospace and defense companies to transition from traditional tin lead solders to EU-compliant lead-free solders for printed board assembly processing. So that is fantastic to have an expert in the field here and to share more information about IPC standards. John, thank you for your time, and both Aaron and I and the attendees look forward to learn more. It's all yours.
Okay, well, good morning and good afternoon. Welcome to the exciting world of navigating IPC standards. I use the word exciting because I'm sure for most of you, the first word that comes to mind when you think of standards is exciting, right? So this is standards identification made mostly easy. I'm going to go through some of the tools that IPC has traditionally provided to aid people in identifying IPC standards. I'm going to show where those tools have some shortcomings for those of you who are still in college, engineering students and not yet in the workforce. I'm going to go over a classification system that we have for our standards that's going to kind of help clear the air a little bit. Then go over to some of the exceptions to those, because as in life, whenever you're trying to standardize something, you'll always find people who make exceptions. And then I'm going to show you some new tools that we've come up with to try and make navigating our standards and identifying standards of interest to you, make those easier. And then lastly, show a path for how you can reach out to IPC staff for questions on standards and ultimately get involved in IPC standards development. That may seem a little scary or daunting, but as I'll go through the presentation, you'll find that it's not so scary to be part of IPC standards group and actually contribute to the development of these documents. So, okay, our active standards, I like to call it a maze. We have roughly 95 standards groups within IPC. Wow, 95. They consist of general committees. Those are generally oversight groups. They don't really work on a standard. They're part of an executive committee that establishes policy for standards and approves standards projects. So they're kind of like, they're like Congress, really. Then we have subcommittees that are responsible for a standard, or maybe they themselves are an oversight body for a specific technical section. And then you have task groups, and this is where the bulk of our standards work is done. You have task groups that are responsible for one or more IPC standards. And within all those groups, there's approximately 125 of them that are active within the overall group of 300 standards that IPC's put together since the 1960s. And yes, I said 125. Some of them are revised on the order of every 3 to 5 years, depending on the popularity. A bunch of them, more than half, they don't typically get updated until like every 5 or 10 years or even later than that, but they're still industry active, they're still relevant, they're still used in the industry. It's just that the technology hasn't advanced much to warrant their revision. But navigating through all of these and finding the right one that's of interest to you, whether you're in college or looking to get out in the workforce, it's kind of like going through this thing. It's a bit of a maze, and you don't even have to be stalked by Jack Nicholson in this thing to have trouble finding IPC standards. So if your focus is electrical, chemical, material, mechanical, or any other engineering IPC discipline, how can you determine what standards or standards groups IPC has that is of interest to you while you're in college, and then potentially help maybe make a decision as to where to go in the workforce or when you enter the workforce, what standards you're likely to use and reference. Maybe you say, hey, I like the idea of shock and drop testing, right? We hook up some board assemblies to an apparatus, it lifts it up, it slams it back down to the ground. And I like the idea of trying to break the heck out of board assemblies and seeing what makes them break, replicating the type of shock and stress that they'll see after they're made, they're shipped, they're handled in use environments. Maybe I like the idea of getting down to the component level. Maybe I like the idea of seeing what happens when you hook up some sensors to a device and see what it takes to make that component pop off the board. In this particular example, you can see in the lower right, you've got two of the traditional surface mount devices where you can see some of the silver colored lead terminations extending away from the body to actually solder it to the component. And in the middle, the device that's actually hooked up is what's traditionally called a ball grid array or BGA device, where all the solder connections are solder balls in an array matrix format underneath the component. Can't see them visually from top down. And that helps reduce the overall footprint of attaching the component to the board if you're pressed for real estate space on the board. Maybe I like the idea of doing some solderability tests. I want to evaluate the ability of the lands and the connection points and the conductors on the printed board that ultimately will be soldered to. I like to determine their solderability. Here's an example of taking a coupon. A coupon is just a fancy name for a small circuit board that represents the overall larger circuit board that's being manufactured and used in final product. Has all the types of holes and attachment lands and conductors that you would see on the actual boards. And this is an example where it's dipped into a molten bath of hot solder, and you just kind of sit there and watch that molten solder and see if it slowly wicks up onto those pads. And so you can measure the wettability of the solder. Maybe you're interested in those kind of technologies. Perhaps you're interested in schematics. You might say, hey, I'm a CAD CAM person. I like to deal with the CAD systems, the design systems, the board layout. So either way, where do you go to find a standard or standards of interest? Well, we have the old way in IPC, which is, oh my goodness, what is this? Yikes, this is the traditional IPC standard specification tree. It's categorized, the documents are categorized by their scope, and then there's a color code that we assign to it to identify which liaisons in the IPC tech department are responsible for them, and you can see their email address in the lower corner. Mine, of course, are the ones in the green. But can you say way too many colors? The first time that this was completed, the first time I saw this in its completed form, I thought I was going to have a seizure. The only time I want to see this many colors is when I'm either coloring Easter eggs with my daughters or watching the last 10 minutes of 2001: A Space Odyssey. So not to disparage this tree too much, it's very useful for determining who the IPC staff person is that you want to reach out to ask about the standard. But from the perspective of being an engineering student and trying to identify what is a standard of interest, this particular tool is a serious Debbie Downer. It's not a good place to start with. It's a good place to go to once you're familiar with the content of a standard. Some other ways we've had a committee homepage on our website. This is a good place if you want to go and find out what the charter is of a group, what their scope is, what kind of documents they might have ownership for, who the leaders are. But again, a rather daunting tool to use if it's a starting point for trying to identify a good IPC standard. And I'm just showing here an example. This is just 3 committees. You see the general committee, you see the subcommittees and the task groups underneath, their names. Some of the task group names actually describe the number of the standard, others don't. But you can click on these on our website and find more information about the charter of the group and who's leading it. But again, not a good way as a starting point to find a relevant IPC standard. So we do have some other ways, and more recently, I've been very excited with the IPC Education Foundation that we've had and developed over the last few years. Really excited to see that kind of connection path between students and IPC that you can get involved with before going into the workforce. There's some online courses which you can take to learn about some of the standards. Obviously, you get a nice certificate when you complete the course. Here are some examples of them: solder joints for surface mount devices, your wire harness assembly, hand soldering. The thing I'll mention about these is the 9 of these at present are mostly focused around printed board assembly processing. So if you're interested in circuit board design, the materials and the processes used to make the bare board before it's actually sent off for assembly, component assembly, most of these don't really cover those. So, you know, they're mostly assembly centric. We also have the IPC Emerging Engineers Program. This is a great system for pairing up with a professional, somebody who's already out there in the industry, shadowing along them. An example is tagging along with them at our IPC Apex Expo event that we hold annually in San Diego, where you can go to some of the standards with meetings with them. You can go and visit the exhibit hall and see all the products that are being used in the industry. This is a great tool for networking with other rising professionals in the Emerging Engineer Program, where you can kind of see, you know, oh, hey, you're shadowing somebody from this defense contractor or somebody from this solder supplier, and you can talk with them and get an idea of what they're learning from their mentors. But for those of you who are in college trying to identify IPC standards, the limitation of this is that it has a limited number of annual slots. There's a fixed number of emerging engineers that are allowed per year. So this isn't an ideal tool for everybody who's curious about IPC standards. So with all that said, there's got to be a better way to find out about what IPC standards are of interest to me based on my college discipline, what I think I might be working with when I get into the workforce. Yes, there is another, and it is the IPC Standards Classification Codes. We actually have a code system. It's intended to address everything from circuit board design through fabrication of the bare board. It's component assembly, assembling all the devices, the surface mount devices, the through-hole devices, the cables, the wire harnesses, the connectors, and then tests that deal with all of those three phases: tests in design, tests in fabrication, tests in assembly. And it makes use of a 4-digit document numbering system where you use the first number to denote a series. So you can have a 1000 series, a 2000 series. So we have 9 different categories. I'm not going to go through all of these. I'm just going to give, I'm going to cover a few of them as examples. This is the part of the presentation where, as I go through the series of documents, some of it will get a little technical. Some of the slides I'm going to kind of glean over. I'm not going to focus on all the technical aspects in the interest of time. So I might kind of talk a little fast or a little faster as I go through these. And if you have any questions on them, at the end of the presentation, you'll see my email address. Feel free to contact me with any questions about any of these standards that we might be going through. So we'll start with the 2000 series. The 2000 series addresses anything to do with the design of the board, whether it's the schematic design or the actual, creating the documents for how the design is supposed to be laid out, the actual CAD/CAM design. We have a 2221. It's our generic board standard on design, the layout, guidance on selecting the materials, how you're going to route your conductors, effective conductor spacing, even going to talk about test coupons or test samples. And you'll hear this word test coupon throughout IPC. If you're not already familiar with it, test coupon, all that is, we're not talking about something in your Sunday flyer for the local grocery store. We're talking about a very small circuit board, usually somewhere like an inch square or maybe ½ an inch by 2 inches in dimension. And it is a small circuit board that has features on it that is representative of the larger production circuit board. Because a lot of the tests that are done to validate the circuit board or validate the assembly, a lot of those tests can be destructive, where you're doing something where it's rendered unusable after the test. And maybe if you're making 1,000 circuit boards in a production run, you don't mind taking out one of the actual boards that are going to be used or sold and test the heck out of that. But if you're only making 25 circuit boards for a customer, you don't want to have to take out one or more of those circuit boards and beat the heck out of them and break them to validate the whole run. You do that to a test coupon, which is a representative sample. So that standard goes into test coupon design. We have some sectionals underneath it that deal with some specific technologies. 2222, that's where you're dealing with your rigid circuit boards. Talks about routing and scoring. So if you have a panel that has multiple printed boards in it, they're actually, they're going to have to be removed, and you want to make sure that the removal process doesn't physically damage the circuit board. So you need to do effective routing and scoring to be able to remove those safely off the panel. The design documents also talk about the relationship between the hole and the lead. If you got a through-hole device, a pin, so you're inserting a pin, you're soldering a lead into the board, because there are still a lot of designs out there that make use of through-hole technology, even though surface mount technology has been around for a long time. So this standard talks about the tolerances and the relationship between the holes and the leads. We have a flexible design standard, 2223. So the example I'm showing on the right, the green are the rigid layers, the typical rigid circuit board. The orange and the yellow are your flexible layers, your flexible dielectrics and adhesives. And then the photograph you see to the left of that is a photographic example of two rigid circuit boards that are joined by a flex circuits, and then they're folded over one another. So that's a ideal solution if you're dealing with constraints on the space that you're going to put those boards in. In fact, I'm not suggesting you do it, but if you were to take apart your smartphone and look inside, you'll most likely find this kind of configuration where you have a pair of rigid circuit boards that are folded over one another and connected by flex circuits. We also have a design standard that deals with something called high density interconnect and deals with something called microvias. And if you're like me, when you first got into our industry, you're like, what is a via and what in the world is a microvia? A via is simply a hole drilled into a circuit board and subsequently plated. It may go all the way through the board. It may go only partially through the board, like what we call a blind via in the upper left here. It may be a whole structure that you drilled all the way through, but then you added additional layers on the top and the bottom of the board, and what was originally a through-hole structure now becomes a buried structure because you can't see it from either side looking at the finished board. So a via is simply a hole with plating that you're not going to insert a component to, you're not going to solder a lead into it, you're not going to stick a pin to it. Its only purpose is to route an electrical signal from one conductor on one layer to another. So it's a path, it's an electrical path. And a microvia is a very small version of those holes, and there's ways to do it by either laser drilling or mechanical drilling. So we have standards that talk about using those types of very small structures, particularly when you're dealing with very, very small circuit boards. An example would be a circuit board that you're going to put in an implantable medical device. So really small boards. That's the 2000 series. 4000 series, this is all the series that the standards that deal with materials used to fabricate the printed board. 4101 is a specification for base materials for rigid boards. So it's going to have all kinds of tests, a lot of mechanical tests, some electrical tests, some chemical tests, evaluating the flexural strength of the laminate material, its coefficient of thermal expansion, both in the XY axis and also in the vertical axis, or what we call Z axis. So it's going to evaluate the CT of the material and how much it expands or contracts under temperature. Obviously, when you're assembling circuit boards, you're putting them under a huge temperature excursion, and of course where the board's going to operate in its operating life. It's an aircraft being subjected to extreme temperature changes, extreme cold at high altitudes, sitting on a runway in Phoenix in the middle of July for 3 hours before getting the clearance to take off. So these boards can be subjected to a lot of stresses. Most of these rigid materials are based on an epoxy woven glass weave structure. And because it's glass and glass base, there is a glass transition temperature, a temperature at which that rigid board, the laminate material, which obviously you use to create all your layers and lay down all your conductors and the individual layers. There's a temperature at which that rigid material reaches a T sub G where it starts to gel and become liquid again. And that's not good for a circuit board. The laminate layers, in addition to being the foundation and the substrate for the circuit board, where you're laying down your conductors and your lands for attaching devices, your layers also have a dielectric strength property. They're not just layers for routing conductors, they're also layers that have electrical insulating properties meant to prevent that material from itself becoming electrically conductive and routing signals where they're not supposed to go. And we have other material specifications, high speed, high frequency, and if you can say it with me real fast, polytetrafluoroethylene, otherwise known as PTFE, otherwise known as Teflon. So a lot of circuit boards that are used for high frequency applications are actually, the substrate material is Teflon based. We have a 4200 series that deals with the flexible laminate materials for flex or rigid flex boards. Let's say the board's been fabricated. You have fabricated the circuit board. You're going to ship it off to the customer. How long does it take before that circuit board is actually assembled? Could be days, could be weeks, could be months, could be years. The conductors and the lands on those boards, you want to preserve their ability to remain solderable, even if the boards have been in storage for weeks, months, or years. So oftentimes what fabricators will do is put some kind of protective conductive pattern plating on the conductors and the lands and the holes on either side of the circuit board. Some popular methods are electroless nickel immersion gold. We call it ENIG, immersion silver, immersion tin. Here's another one, INIPEG. It's a nickel, palladium, gold composition. And again, this can be laid down on the conductor patterns to protect the bare copper from oxidizing and to protect the solderability of the attachment points, the attachment lands while the circuit board is in storage. And these specifications provide a series of tests to validate their effectiveness, validating the thickness by what's called XRF, X-ray fluorescence, maintaining their solderability tests, evaluating embrittlement. There's a little thing called nickel hypercorrosion with ENIG and INIPEG. I'm not going to go into great detail of that, but that is an example of a corrosive function that can happen to the plating that inhibits its solderability, so you want to test for that. So there's the 4000 series for materials. 6000 series is once the board's actually been fabricated, actually performing a visual and structural integrity evaluation of the finished circuit board, looking at making sure the conductor widths were manufactured properly, that you have adequate spacing between the conductors. Visually, do you see any damage on the board? Do you see evidence of delamination from the surface where some of the layers may have separated? And then lastly, we're going to take those coupons. So here's another example where we use a coupon. Again, a physical small representation of the overall larger board. And we're going to thermally stress the heck out of this. We're going to subject it to hot and cold temperatures over a series of cycles, maybe like 6 cycles or more. And it's meant to replicate the thermal excursions that the board itself will go through throughout its life, throughout the assembly process. If it's going through a conveyorized reflow oven to make the solder joint connections, it might have to go through a wave solder machine if you've got some through-hole parts. Maybe you might have to do some hand soldering of components, or if the product's been out in the field and something happened to it in the field and it comes back and it needs to be repaired, you might do some additional hand soldering to remove a device and add a new one. All those individual processes are thermal excursions that the board is being subjected to that could impact the reliability of the board. So we thermally stress the samples and then we cut them up with a diamond saw and get this guy over here. So you cut it up and now you can perform a cross-sectional analysis and look at the guts of the hole structures and the internal layers of conductors. And now you can perform a structural integrity analysis and look at the cross-section of those holes. These are typically performed anywhere between 100 and 400x. Look for voids and cracks and folds in the plating. IPC has a lot of member companies that are test labs that do look at this kind of stuff all day long, every day. There are some circuit board shops that actually have in-house testing to be able to do this kind of thing, to create microsections, evaluate them in-house. Others, like I said, need to send them off to a third-party test lab. And it's basically looking at the integrity of the inside of the circuit board and all the holes that they're either through holes or they're buried in the board or they only go partially through the board. And then we have, just like with the other series, we've got other specs in that series that deal with the flex board. Yeah, this is not so good. Got some scratches on this guy. I mentioned that flex transition zone where you've got the transition between the rigid section and the flex, and oops, maybe you got some adhesive that's squeezed out. You see that shiny stuff? That's not so good. And then of course we have specifications that deal with those high frequency boards that are Teflon based. So that's the 6000 series. We're now going to get into the 7000 series. So the series I've mentioned so far, the design series, the material series, the board performance, those are all specifications, something that's called out in a contract. The 7000 series deals with the components, that are going to be soldered to the board. This series is not a series of specifications. They're more like guidelines. They're each like between 100 and 400 pages. A lot of it is narrative, tutorial instruction on the technology and its use in assembly. So you have IPC 7093. These are what are called bottom termination components. So you don't have leads. You don't have soldered lead terminations coming out from 2 or 4 sides of the board, of the component, I should say. So all the connection points, the soldered connection points, are actually underneath inside the body of the package. Then you have a document that deals with what we call flip chip. This is where you've got the die element is not encapsulated in any kind of plastic body. The bare die is attached to another device that's then attached to the board. And then you have standards for ball grid array devices, like I said, where you have a matrix of solder balls on the bottom of the package. And those are really a subset of bottom termination components. So these 3 documents, they're not specifications. They basically go through what the components are like, what it's like to assemble them, some of the typical reliability issues that you'll encounter in utilizing them. In the case of BGAs, maybe you got some voids in some of the solder balls. Is having voids in that solder ball a good thing or a bad thing? Does it affect its reliability? And then lastly, I talk about the global and the local expansion mismatch. So you heard me mention earlier about the laminate material. The board has a CTE, coefficient of thermal expansion. The components have their own CTE, and both of them expand and contract under stress and temperature. And obviously you want your components and the circuit board they're attached to have CTEs that are pretty close to each other. If you don't, then they are each expanding and contracting under their own, under temperature, and now that is a reliability issue that could result in the part, separating from the board. Which leads us to the 9000 series, quality and reliability. This series deals a lot with assemblies and subjecting them to all kinds of tests to evaluate their long-term reliability. So you absolutely positively want to determine the long-term reliability of all those surface mount devices that you have soldered to your board assembly. This document's going to say, I'm going to give you some tests. And if you look here in the upper right, some of these tests, you got a thermal profile from -40 to 125 C, and you might do that for 200 cycles, or oh my, 6,000 cycles. So these are tests that will typically run days, weeks, or months in a chamber, going through all these thermal excursions, basically to replicate the kind of thermal excursions that the assembly is expected to see throughout its life out in the field over the course of many years. So this is basically accelerated life testing. We have another document in the 9000 series. This is a bend test. So you're basically taking an assembly and you're putting some pressure on it and you're bending the heck out of it and waiting to see what's going to make those components crack and fracture and come off the board. And you may recall early in the presentation, I talked about shock and drop. We have a standard that deals with that. So whether you're testing the overall system in its complete box system in whatever product it's going to be fielded in, or the assembly, or maybe you're just trying to address a single type of component. We have arm testers, drop platform testers, quick release, high acceleration shock testers. So if you know the product's going to be operating, maybe it's going to be in an avionics package in a military aircraft or in something that's going to go out into space, and you know that it's going to be subjected to high Gs either for a launch or throughout its life cycle, and you want to test its ability to operate properly. And as I mentioned in the previous slide, there may be some strain between the component itself and the board that it's attached to based on their CTE values, and we have documents to talk about testing the strain and what might make it pop off. Okay, So all of our standards are designated in this classification system, right? Well, no. And now it's at the point where you're like, oh, you got to be kidding me, John. You tell me we got all these nice series that clearly identify. You got 2,000 series for design and 4,000 for materials. Yes, we still have some standards, some major IPC standards that fall outside of that 4-digit numbering scheme. And some of the reasons that they do is the immense popularity and usage of them in the industry. They've been out there for a very long time. They have name recognition, brand recognition. Maybe we develop them jointly with other standards organizations. If it's a standard that's widely used and there's a lot of references to it, there may be a significant cost to the OEM customer to update all their drawings and their procurement documentation to reference a new number. They don't want to really go through the cost of updating all their drawings just for the sake of a document number change. And the standard might be associated with a cert program. I'll give you an example. One of the documents I'm responsible for is the T50. It's our terms and definitions standard. It's kind of like the Webster's of our industry. You hear any term that I'm using in this presentation, or when you're looking through any IPC standards, you can go here and get the definition for it. I made an attempt to change it from T50 to IPC 1901, followed that classification system. I was naive enough, this was in my early years at IPC, and I thought this was going to be widely adopted. The reaction I got to suggesting that we change the document number was as if I was doing this. All right? And people came back and said, do not push that button. T50 being a terms and definition document, it's proliferated heavily throughout our standards as a reference document. And the industry came back and said, you realize how many drawings we would have to update to change the designation from T50 to 1901? So I got a lot of pushback, and so that was enough to justify retaining the document number. And so that's an example where things fall outside that classification code. So the next couple of slides are going to talk about the two other categories of standards. One of them are called the J standards. So they all start with the letter J. The other is A for acceptability. So we're going to introduce the J standards. Don't think JV, they're not junior. J standard 001. This is our second most widely used standard. So this is the document that deals with the actual assembly of the circuit board. It actually has the requirements for once you've assembled and soldered components onto the board, how do you verify that they have a good solder joint connection for the type of device? On the left-hand side, we show some gull-wing lead devices. On the right-hand side, these are those bottom termination components I mentioned, where the attachment point is actually underneath the body of the device. The document also talks about cleaning requirements for removing all those processing chemistries. There's this little thing called solder flux, which I'll talk about in another slide. We have what's called conformal coating materials, which is the deposition of a transparent material. It's deposited in liquid form, and it basically conforms to everything on the circuit board, all the devices, the board, so it literally conforms to the circuit board. It's transparent, can't really see it when it's done, but it helps provide protection against moisture and against other processing chemistries and dirt and whatnot in the finished board. So some other J standards. You're at a company where they have purchased a lot of components that they're ultimately going to solder to some boards, but they're sitting in boxes or tubs or tape and reels or trays for months or years. How do you know that those components, the lead terminations on those devices, how do you know that they're going to be solderable months, weeks, years after they've been sitting in storage? This document gives you some tests. Maybe you're dipping it into a solder bath. Maybe you're putting it into that hot molten bath of solder and watching the solder wick up. I showed that earlier at the beginning of the presentation. You know, here's an example of a terminal that is not clearly solderable. Got a lot of problems with this one. J standard 003 is solderability for the board itself. So after the board's been fabricated, maybe the board's been put into storage. Particularly circuit boards that are going to be used by DoD or defense, those bare circuit boards may sit in storage for years before they're actually brought out for assembly and then shipping to the customer. So how do you want to know that the board itself and all the surfaces that you're going to solder devices to have remained solderable after all these years? So again, the same type of tests. Here's an example of some pads that are used for attaching devices. This is an in-ink board, electroless nickel immersion gold. And if you look here, you can see where some of the solder has obviously made a metallurgical bond with the gold plating, but you can see some spaces where it just did not form a connection. There is no coverage. You tried to put some solder on there and it just seeped away, and so you have some exposed plating. This is an example of what we call non-wetting. And then we have these three documents. And I'm not going to go into extensive detail, but basically they're talking about solder fluxes. And a flux could be something in a liquid form, a paste form, a solder cream. And fluxes are materials that are used primarily to kind of help activate and spur along the solder joint formation process. They can also serve a dual role where they capture some of the contaminants in the assembly process that can then be, the flux can then be washed away and get rid of the contaminants. So you have your solder pastes. Here at the bottom, we have J Standard 006. This is a document for all your solder alloys themselves. Our industry, for many years, the solder alloy of choice was traditional tin lead solder. And if you've paid attention to all the things that are happening with green technology and how the European Union is trying to get the lead out of electronics. They don't want to see lead in electronics. And if you've ever seen photographs of landfills of all the old busted computers and computer parts, they don't want to see lead in landfills for electronics. So they're pushing the electronics industry to stop using tin lead for solder and use other lead-free solders. An example of those are solder alloy compositions that have things like tin, silver, copper, antimony, bismuth, but they're not tin lead. And so they, because they're not tin lead, they have different melting temperatures, which can affect that T sub G that I mentioned for the circuit board, the material. Some of the temperatures that you have to get the circuit board to have that solder melt might adversely affect the laminate of the board. So lead-free solders could be a problem if you're for some of the traditional materials that the industry has used. So all these documents address the solder flux, the solder paste, and ultimately the solder alloys. So that's the J standards. I'm going to mention the A standards, and we are getting close to being done here. So A600, this is acceptability of bare boards. So it's going to repeat the requirements from the 6000 series. It's going to repeat those requirements for the boards, and it's going to supplement them with photographs. The photographs give examples of what's acceptable and what's non-conforming. They don't tell you anything about how many samples you have to perform. Doesn't tell you what happens if you find a non-conforming condition. They're just pictures that says, here's your target, here's what's acceptable, and here's what's non-conforming. I use this as an example. This is what's called de-wetting. And you may have seen in the previous slide, I showed an example of what was called non-wetting, where the solder just would not wet and adhere to the plating. Here, like you can see in the lower left, in this white bordered area, you don't see the gold plating anymore. You don't see the gold surface plating. So you can tell that there's some solder that did wet, but most of it has receded and pooled into a big mound. So you have some very, very thin portions. And then over here on the right, you have so much of that de-wetting that this is considered non-conforming for circuit boards. And then we have this guy here. This is A610. And this is our #1 most widely used standard within IPC. You're likely to hear this number more than anything else amongst IPC standards. Again, it is a visual collection of photographs showing fully assembled boards and showing examples of what's acceptable and not acceptable. Doesn't talk about the assembly operations, doesn't talk about what you do when you find a defect and having to do any repairs. So oftentimes it's used in conjunction with J Standard 1. So I've been showing you some examples of you know, the photographic examples in the document. So we're going to show another one. And what do you think the example might be? Could it possibly be, yeah, our old friend, de-wetting. And this is de-wetting in the fully assembled circuit board. And I don't know if your eye caught this, but you'll kind of notice in the previous slides for the bare board documents, when something's not right, they call it non-conforming. In the assembly documents, when something's not right, they call it defect. So why do you call it non-conforming in one and defect in another? That's a little trivia question. If you like the answer, you can use my email address at the end or email me with what you think is the answer, but it's a little trivia question I threw out there. Lastly, we have a document that deals with cable and wire harnesses. So if you are using some crimping for wires, or you're using actual cable with all its braiding and shielding, this document will give you the acceptance for all the cables and wire harnesses that are used in circuit boards. Okay, so we have gotten through all the documents. Now, do we have a better way of helping you identify where to find standards? And the answer is yes. We've created this IPC Simplified standards tree. This is much easier on the eyes than the one I showed you before. It is structured according to the manufacturing process, albeit right now it's kind of from the bottom up. So if you look in the center of the track, the principal documents are provided in this tree. You've got a basic color scheme, so you have green for design, and you can see the 2220 series I mentioned. Your blue is all your base materials, everything that you're using to build the bare circuit board. You can see the 6000 series, and the yellow are everything dealing with the assembly and soldering of the circuit board. And on either side, on the far left and the far right, we have these ancillary supporting documents, and they are shown in their proper place within the manufacturing process. So if you look over here, right here in the middle, in the bare circuit board section, here's that IPC 6000 series I mentioned. And then over here, you can see here's those 4500 series documents that I mentioned about all the different types of surface finishes, your electroless nickel immersion gold, immersion silver, immersion tin. All those documents I mentioned here in the upper left that you're using for doing all kinds of testing like shock and drop and vibration and mechanical bending for the assemblies, they're shown here. So this is a much better tool to use. We're going to be modifying it further in the future. We're going to kind of flip it over on its head. So when you go from the top to the bottom, you're starting with the design and working all the way to assembly and final inspection and putting in whatever box it's ultimately going to be in. We're interested in your feedback on this as we modify this as students in college and maybe not yet in the workforce. We're interested in your feedback on whether you think this is a better tool for identifying standards and how we might be able to tweak it. And that being said, we do not mind hearing from you. I'm throwing this up here. This is something that I would like you to remember. This is answers@ipc.org. Do not hesitate to use this tool. Do not hesitate to use this email address. Don't feel like, well, I'm not in the workforce, I'm in college, I still don't know a lot about all this technology, I'm kind of hesitant to contact us. Don't. This is a resource for all questions related to IPC standards. It's monitored by our staff daily. We field technical questions on existing standards. Maybe somebody's asking where something is in a standard. Maybe somebody's looking at a particular requirement and saying, hey, we have a customer and a supplier who's having a disagreement or a conflict in understanding the interpretation of requirement. Can you, IPC, provide an adequate interpretation of this requirement? Where can I find the right standard? You say, John, I've used all the tools you've shown me in this presentation, and I still can't find what I'm looking for. Absolutely use this email address. We're willing to answer any questions about any standards that you're interested in. Maybe you want to know when one's about to be published. Maybe you're interested in joining a standards group, and what does it take to get a new standard group started for something that we haven't addressed in the future. So this tool, this address is flippin' sweet. And I'm going to wrap up with talking about standards development participation. This is what IPC is for. This is why we've been in existence for over 60 years. It's standards development participation. It's all done voluntarily. It is your peers in the industry. And you can have a voice in shaping our standards and the revisions of those standards. And it doesn't matter if you're somebody in college. It doesn't matter if you're somebody who just entered the workforce for a year. It doesn't matter if it's somebody who's been an industry veteran for 30 years. You can have an equal voice regardless of your level of experience in industry. You can have an equal voice in helping to shape the standards and contributing to their development. And our standards development is really one of the few places where it's collaborative competition. You have people in these committees who, outside of IPC, outside of the meetings, they are rivals in the industry. They're competitors. But we get them together and they actually collaborate collectively on a standard that's for the benefit of everybody. And one of the unique things about our standards development is industry recognition, right? We like to recognize and award the people who have participated in our standards. It's also a path to develop lifetime relationships with people in our industry. I like to reference a chair for one of my groups. He's in his early 30s now. When he joined IPC and became a chair for one of my committees, he was in his late 20s. In that time, he has worked for a rigid circuit board shop in Ohio, worked for a flexible circuit board shop in Minnesota, worked for a laminate manufacturer in Sunnyvale, California, and most recently transitioned to an OEM defense contractor in Colorado. And even though he's jumped jobs, and I call him a nomad, he is still on the IPC committees. He remains on the committees. He still participates on the standards. He is a colleague of mine who I will probably be a lifetime friend with. So that's one of the things that you'll find in joining IPC committees. Not only peers, not only getting technical information, but you're going to find people who you may develop a lifetime friendship with. And that's one of the things that I love about IPC, and that's really why I've been here for over 21 years. So that is a wrap. I'm open to any questions, and here's my email address. I encourage you to contact me with any question you have about any of the standards. If I can't answer it, I can find the right person in our standards department who can. So thank you for your time.
Thank you, John. That was incredibly informative. I look forward to bringing this information to the rest of the students. I do have a couple questions, so I will start with the one with the Q&A. How many working groups are responsible for the IPC 2000 series of standards?
Okay, so for the 2000 series, that is probably, I would say, we have the 22, yes, let me backtrack. We have the 2221, 2222, that's managed by one group. 2223, which is Flex, that's a second group. The 2226, which is HDI, that's a third group. So the 2220 series standards alone, you've got three different groups. We have a new one that's working on a high-speed document that we haven't published yet, so that's 4. That's within the standards that talk about the actual design of the circuit board. If you include the other 2000 series documents that deal with like product documentation, how do you accurately build a drawing? What's the rules for developing a schematic drawing, and proper rules, symbology, electrical symbols that are used in the drawings, and the board procurement documentation? That's probably another 5 or 6 groups. So overall, in the whole 2000 series, I'd probably say there's about a dozen groups, dozen committees right now.
Very good, thank you. And how does one go about joining standards committee? Do they contact answers at IPC?
That is the best way to do it.
Okay.
As I said, we monitor it daily. Most of us in the tech department look at it. I saw 2 emails in there yesterday from college students at 2 universities here in the U.S. One of them was just asking about what kind of standards address a particular technology, and the other one was, hey, how do I get involved? How do I join a standards group and have a voice while I'm in college and then when I get into the workforce? So that's a good, definitely answers.
That's awesome. It's not something that we marketed heavily to students in the past, but we're getting more students learning more about the standards and interested in potentially joining the committees. So I'm
seeing that, right?
Yeah.
So like I said, yesterday we had 2 emails alone yesterday from college students, and I'm seeing more and more engineering students using that tool to ask us questions. And there is no such thing as a dumb question. Any kind of technical question. Somebody asked me the other day, do we have standards that deal with credit cards, right? The chips that they're not putting in credit cards. Do any of our standards deal with RF chip technology? There's no wrong question to be posted to that address.
Interesting. Never thought of that. All right, I've got another question here. Is there a standard set up for PCB design rules that can be incorporated into CAD programs? Something that pulls in from other standards?
Yes. It is we have the IPC 2580 series, And essentially the 2500 series, that's all your data transfer language. If you're talking about conveying design information from the CAD systems to the manufacturing CAM systems at the fabricator. So there's standards that talk about the design languages that are used from design to manufacturing. We even have some standards that talk about the language that's used for assembly equipment to communicate with one another electronically. So if you have in your assembly line, you have the equipment that's picking all the components out of the tapes and reel trays, depositing solder paste on the components, and then you have another device where those boards are actually going through the conveyorized reflow oven to be soldered, and maybe they go through a subsequent oven for wave soldering, and so you've got 3-4 different machines. They're all connected, and we provide standards that talk about how they can communicate with, automatically with one another.
Any other questions? I don't have any in the chat or in the Q&A.
Yeah, so again, if you want to formulate a question and send it either to me directly with the email address at the end or to answers@ipc.org, either will work.
Okay, seeing no more questions right now, just want to remind everybody, as one of my colleagues posted in the chat, this webinar will be recorded. We'll put it on our YouTube channel, and you can also view past webinars on ipcef.org/webinars. And I really would like to thank John Perry. This was an incredible presentation, very informative. I'm eager to get more students watching this and learning more about IPC standards. This is a great resource for them.
And I'll thank those of you students who attended this presentation. Like I said, you're going to be the next generation of voices that represent what kind of standards IPC shapes and how we revise them. And don't feel. I know the name standards can be kind of nerve-wracking, may sound kind of boring, but you'll find that if you join a standards group, it's very open. They're open to your input, even if you're not a 15, 30-year industry veteran, and you'll find quickly that you will develop not only colleagues and peers in the workforce, but you will develop lifetime relationships with some of these folks.
All right, fantastic.
Excellent. Thank you so much, John. Thanks, Aaron, for driving it. Thanks to all the attendees. Hope you all have a great rest of your week.
All right, thank you.